I would like to turn it over to my other friend and colleague, Professor Clayton Miller from National University of Singapore, as we get a bit deeper onto the subject of machine learning and how it applies to the digital transformation of the built environment. Clayton, all yours.
Great, thank you, Kostas, and once again, yeah, thank you for the invite to this workshop. I'm really happy to share some of my viewpoints, and yeah, I think the previous two presentations tie nicely into what I'll be talking about, which is getting into the subject of data-driven modeling, machine learning, and I'm going to be talking about a few areas of improvement that I think we can make in the built environment as compared to what some of the other sort of industries out there. So first off, yeah, I'm also part of the Department of the Built Environment, like Adrian Chong, who just presented. And the team that I'm a part of is called the BUDS Lab, the Building and Urban Data Science Lab. And we're kind of a team of architects, engineers, computer scientists, data scientists. So like a really multidisciplinary team of researchers looking at different ways to transform mostly measured data, but a little bit of simulated data as well, into value related to energy, thermal comfort, and things like that. So yes, I'm going to talk about machine learning. This is a nice graphic from last year's, an economist from last year, really showing the explosion of investment, of research on the left and the right-hand sides of this graphic. You see kind of the increase in focus of using machine learning / AI for various within industry, basically. And then the chart in the middle is really showing the breakdown of different applications in the various industries as a percentage of the total investment. And right at the top of the list, you have autonomous driving. This ties really nicely into the analogy that Stefano was making earlier about Tesla. I'm also going to tie into that analogy as well. Because, you know, autonomous driving as an example is kind of similar to the built environment in some ways. You have a kind of a machine or a car that it's a convergence of traditional sort of engineering design process with the potential for, you know, data-driven models. And then as well, there's occupants. There's occupants in buildings, there's occupants in cars. And so there are safety operational issues. There are a system of networks, which are roads, for the example of a car, and then buildings and cities, for the example of buildings. So there's a little bit of a comparison there, I think. But there is a huge difference in the amount of investment that's going into AI applications for the autonomous vehicle field. So the car industry in general, basically. And this is a graphic and kind of website that I found that tried to quantify that. They're saying that either invested or planned to be invested amongst the major players of the automobile industry. So there's $100 billion of investment planned in AI with a focus on autonomous vehicles. So getting cars to basically drive themselves. So this is a lot of investment. It's the largest percentage of total investment in AI. So the question is, okay, why so much money? Why is there so much money going into this field? And of course, there's a need for autonomous vehicles. But there's also a very strong foundation. So how did autonomous driving become the application with the most investment? So keeping people safe, of course, having cars that drive themselves reduces a lot of the costs that a lot of organizations have, things like that. But there's also an AI and machine learning foundation to autonomous driving and autonomous vehicles. And the key component of that foundation is computer vision. So a car, in order to be able to drive itself, needs to kind of, quote unquote, see where it's going and see what's ahead of it. And here is a screenshot from a YouTube video from Tesla, from one of their machine learning experts talking about deep learning. And it's really showing, you know, the types of things that an autonomous vehicle needs to see and identify, recognize, process, and transmit basically all of that knowledge into its control, in a sense. So getting the car to go where it wants to go. And computer vision is a field that didn't just spring up overnight due to this need or because of autonomous vehicles. It's been actually quite a long process. And this, I'm not going to go into the details of this slide. This is actually a graphic put together. There's a link down at the bottom that you can follow to find the reference of this. On the top of this graphic, you see these green boxes. These are kind of the industry transformations that occur due to computer vision innovation. On the bottom, and of course in the middle, you see this timeline, and it's not that long ago. Actually, 2011 is, of course, there's the 1980s and 40s and things like that, but really where you start to see a lot of the black boxes on the bottom is in 2012. So it's not that long ago. It's less than 10 years ago when machine learning for computer vision really accelerated. And in 2012, you see a box there called AlexNet. AlexNet was basically the invention of what we call deep learning now. And so these technologies are not that old, but they have really accelerated things like autonomous vehicles and other types of computer vision applications quite rapidly, and really brought them to market or commercialized them in very fast ways. So what is, AlexNet, and where did it come from, and those other models that you saw at the bottom? Well, essentially, they all are possible because of a massive data set that was created throughout the 2000s and culminating in its kind of release in 2009. It was a project led by a professor from Stanford University, and she developed this data set and released it in 2009. And by 2011, they started having competitions, which I'll talk about in a second. It's a data set called ImageNet. And on the right-hand side, you can see various things: airplanes, cats, dogs, all these things. And this is over 14 million images of all kinds of things, everything you can think of, with labels. So labels are very important because that's what you use to train models. And this data set has pretty much single-handedly driven a lot of the innovation that I just talked about, because they've used this data set for various competitions over the last a little over 10 years. So 2010 was the first year. They had a competition called the ImageNet Large Scale Visual Recognition Challenge. So a long name, there's an acronym there, but it's a really important competition for the computer vision community. And on the right, you see an Economist article from 2016, even showing that this particular competition, the challengers in the competition every year are getting better and better at recognizing what is a cat, what is a dog, what is an airplane, things like that. And like I said, in 2012, that's really where these deep neural network techniques and deep learning, in a sense, was even invented in this competition. To the point where by 2015, machine learning was doing better than humans at actually recognizing objects and images. So this is really powerful, and this has become one of the big drivers, like I said, of computer vision research and technology. That's not the only machine learning competition out there. There's, in fact, since the last about 12 years, lots of machine learning competitions popping up here and there that try to leverage large data sets to solve big problems in what we call a generalizable way. So if a solution is the best at predicting something across a massive data set as compared to models from hundreds or even thousands of other competitors, you can consider that solution to be interesting, meaningful, and usually it drives innovation in whatever application. So this slide shows on the left another famous competition, one of the first ever out there by Netflix in 2009, where they had a competition for $1 million prize to the team or person that could come up with models that would predict your next the next movie that you would like to watch based on your previous sort of viewing history. $1 million for the winner of the best model of that competition. And since then, there's a website called Kaggle, which you'll also hear about here in a second, which also has had $1 million competitions, and dozens of other competitions that are not $1 million. The top one focused on lung cancer detection. There's one for home value prediction. And at the bottom, you have one for deepfake detection, which is the most recent $1 million competition. So like I said, beyond these $1 million competitions, there's dozens or even hundreds of other competitions focused on all different kinds of applications. And the Kaggle is not the only platform either. There's several other platforms that do these type of competitions as well. Benchmarking datasets. This is the datasets that usually you would use in a competition, and then like a lot of times they'll make their way into the community, and people can use these datasets to compare their solutions, whether it's hardware, software, models, techniques, whatever you name it. People can apply their methods to a dataset that everyone else also applies their solutions to. And so there's a platform called Machine Learning Commons, or ML Commons, which is being driven by a nonprofit, and I took a screenshot there in the lower left-hand corner of a few of the companies behind it. That's really just, I mean, they're in alphabetical order, and I couldn't fill up the entire slide with all the companies, but you get the point. There's a lot of momentum behind this. They've got a lot of open data sets from imaging, from computer vision, but also from sound recognition, people's speech, from medicine, all different kinds of applications that you can imagine in a sense. So, of course, this workshop is about the built environment, not about all these other communities. So how are we doing over here in the built environment? What is it, you know, let's compare ourselves for a second. And this is kind of I guess an exaggeration in some sense. It's not always like this, but in the built environment, especially for machine learning or a lot of things, we love case studies. And it's really a tradition in our field to look at a certain building because the design process, because the operations, analysis, things like that. We love to look at a single building that we have access to, we pull data from. And this kind of ties back into Stefano's point about the lack of scalability of collecting data from lots of buildings anyway. But what we find a lot in our community is I've got my case study, I've performed machine learning on it. Of course, my model is amazing. It's fast, accurate, easy to implement. And all of my collaborators and colleagues and people in my community also have the same thing. But what we really need, and you'll see in a few slides, is something more similar to ImageNet. And just to show a quantification of this phenomena, I did a kind of an overview study, a meta study of one of the big reviews out there that came out in 2018. And one of the applications in that review is long-term energy prediction, which is most often used in measurement and verification, where you're building a machine learning model based on what's called a baseline energy data, your training data in a sense, and you're predicting a test or reporting period. And then there's a certain point where there's an energy saving intervention implemented on a building. And of course, the building goes into a different mode of operation, and the green line shows what that is. And you're basically using your test data from your model to compare to what actually did happen to get the energy savings of that project. So long-term energy prediction is pretty common, and it's used quite a bit in measurement and verification. On the right-hand side, you can see from this review, all of the studies that I found from that review, where most of them, 33 out of 42 of them, are creating models for a single building. So they're really focused on a very, very small data set. And what you often end up with is something called overfitting, where you're basically creating a model that's very special and specific to that case, but would not generalize well across other buildings and therefore wouldn't win a competition if there was one. And so my mission since the last 5 years is 2 points: to figure out a way that we can become more like the autonomous vehicle industry, focus on machine learning in ways that make it more scalable and generalizable, and at the same time, try to figure out a way to get our research community, our industry, the professionals in our industry to learn from the rapidly expanding machine learning and data science communities. Essentially creating something like ImageNet for buildings, for the built environment, where you can apply your model, your algorithm to a number of buildings and essentially know that your model is somewhat generalizable, but also sometimes more importantly is that your other people in the community can also apply their techniques and there can be an actual comparison between techniques. So you might think that we're behind autonomous vehicles, but actually at one point we were pretty far ahead of the game. Back in 1993 and 1994, ASHRAE actually sponsored what's called the Great Energy Predictor Shootout 1 and 2, led by two professors, Jan Kreider and Jeff Haberl, who you can see there. And back in those days, it was a much smaller data set. And a really nice little anecdote from the competition was that if you wanted to participate, you had to give those guys a call, they didn't use email apparently, and they would mail you a floppy disk, a big one, not even a small one, a big floppy disk with the data. You would run your models, you'd put the data back on the disk, and you'd send it back to them. So we were ahead of the game in the built environment way back in the days, even before the internet, but we lost track of that. So we haven't had anything like this for a long time. So in 2018 and 2019, I was part of a team also led by ASHRAE with one of the old school founders. Jeff Haberl as well was involved, and as well as many other people, which I'll mention at the end of the presentation. And we put together a plan to launch a new machine learning competition on the Kaggle platform, but this time using data from almost 1,500 buildings from across North America and Europe, which was about 2,380 meters. And these are whole building electricity, chilled water, or hot water meters. And the idea was that the contestants in the competition on the Kaggle platform would download our training data set, make their simulations and predictions, and upload their predictions to the platform. And then instantaneously, as soon as they upload a prediction, they're placed on a leaderboard. And they could make up to 2 submissions per day across the roughly 60-day competition, to kind of see like how they can improve their models and how they can compete against each other, and basically who could basically make the best machine learning workflow for this long-term energy prediction context that we pose to them. And so this was late 2019, early 2020. We had lots of people participate, over 4,300 participants. They were able to create teams of up to four or five people from all across the world, 94 countries. And like I mentioned, they could submit up to 2 predictions per day to kind of see, you know, how they can improve their models. So we ended up with close to 40,000 total submissions for this data set of 1 year of training data and 2 years of test data of hourly whole building meter data. And the winners were, you can see here, was a bunch of mostly teams, either pairs, teams, or there was third place was an individual. And there was prize money supported by ASHRAE for the contestants who got in the top 5. And in order to sort of get this prize money, they were also obligated to give lots of information about their solution, how they approached the problem, what were the different steps that they used, the pre-processing, post-processing, all the different steps in between, which I'll talk about in a second, and really share this knowledge and code even with the community. As you can see, they're from all across the world. A lot of them are from either their students or they're from the machine learning or data science communities. And like I said, they all shared their full solutions. So if you follow the link, and before I started my presentation, I posted a couple links. One of them is this slide deck. And of course, within the slide deck, you have the links here. And at the bottom of this slide, you can click on that link. And there's a repository that has the top 5 solutions that have been replicated and sort of verified. There's also a lot of links to videos that the winners made, which explain their solutions, how to reproduce them, how they approach different parts of the problem. So a wealth of knowledge that really has brought already the community a lot of value. And just a little bit about these best solutions. Something that I thought was really interesting was, first of all, these were just large ensembles of models. There was no perfect winning model in a sense of, what is the perfect model? Is it a neural network? Is it a gradient boosting tree? What have you? Most of the solutions are ensembles of models, which is very common in practice, but it was not so common in the context of built environment energy prediction. Gradient boosting tree models were by far the most used, and there was a certain package called Light GBM that was used by pretty much all of the contestants in the top 50, which is a very fast version of the gradient boosting model trees. Not a lot of contestants used quote unquote deep learning or neural networks or really fancy neural network models, which was kind of surprising. And pre-processing of training data was really, really important. And so we found that the differentiator of the top teams was how well they prepared the training data set, how much weird or outlier removal behavior did they remove, which gave us an indication that there is a sense of contextual knowledge. You can't just throw data into a model and get the best solution. You need to be able to prepare the data properly, which was really interesting. So of course, there was lots of value in these top 5 models. But also one of the byproducts of these competitions is that lots of people share other types of work. So they can actually share what's called a notebook. And a notebook, a lot of you might be familiar with Jupyter Notebook. So it's a Jupyter Notebook style format where they basically post things that they found, either modeling, pre-process. In the lower right-hand corner, you see pre-processing, the modeling, EDA, so exploratory data analysis, and all different kinds of categories of shared workflows through these notebooks. Over 450 notebooks were shared, all the way from things that would help a beginner all the way to very advanced modeling techniques. And a good example of that is this notebook. This is the most upvoted notebook in the competition, which was a quote unquote gentle introduction to the data set. This is really important for people that are not familiar with the built environment meter data sets, or people from the built environment who are not familiar with using Python or data science or the models or things like that. So come on, check this out. If you don't know how to program, you should definitely check these things out. You can definitely copy and edit these and clone them and learn from them. And one of the things that we're also working on now is really looking at the limitations of machine learning that came out of this context. This is such a big competition with a lot of participants. So we want to see, where did the top models fail? What was the behavior they were not able to pick up? And we categorized that error into these 4 categories, which I won't go into detail about. And there's various solutions potentially to fix these errors or account for these errors. Or maybe the errors are quote unquote out of range, meaning that there probably is no solution to make the models to account for those errors. We just need to be aware that there are such huge disruptions in behavior that a model is just not going to work. As Adrian mentioned, you can't extrapolate data-driven models. And then finally, after the competition, we got together and added a little bit more data that we didn't include in the competition and released the data set as what we call the Building Data Genome 2 project, which is 2 years of whole building meter data from almost 3,000 meters. So there's a few extra buildings, a few extra sites that we weren't able to include in the competition that's included in this data set. So we're trying to move towards ImageNet. We're not even close in a sense in terms of volume of data, but this is one of the efforts towards that. And I don't want to say we're the only ones. In fact, there are dozens or even hundreds of other studies out there that release their data sets. One of the things that we're now working on as part of the International Energy Agency Annex 81 is trying to basically find as many of these open data sets as possible. And I've gone through and reached out to lots of people. I've posted things on LinkedIn, and I've got a lot of responses and taken the data sets that people have supplied or ones that I found and put them on Kaggle as well in the form of what's called Kaggle data sets. And so this is just me posting them. Of course, all the attribution to the authors and the people who generated the data is all there if you want to check it out. But what we're trying to do is create lots of examples of open data sets that people can build on top of. Some of these data sets actually include data from the Cozie Platform, which is the smartwatch-based platform that Stefano mentioned. So there is a little bit of data on there if you're interested in playing around with it from some of our previous work. And this is a project that I also think is really interesting because it's also open source and people can contribute and can deploy their own experiments using the platform and can volunteer to even help with the development of it. So it's a little bit of a tangent, but for the Annex, coming back to the sandbox, the Annex 81 Open Data Sandbox, there are different things that we're planning on doing with these data sets in terms of hackathons, using some of the functions of Kaggle data sets where you can develop what's called tasks, and then people can actually submit solutions to tasks. So please, like I said, if you're interested in this, please check this out. We're also thinking about a great predictor competition 4, which actually goes in the direction of also something Stefano mentioned, which is the brick schema. So we're looking at ways to create a machine learning context around semantic modeling of metadata from buildings. So the other link that I posted in the chat before I got started was a link that if you do have a data set, maybe it's not open yet, maybe you'd like to consider opening it, whatever it may be, please click on that link and fill out a quick Google form. And then I will contact you, or one of my team will contact you, and we'll investigate whether we can add that data set to our library. So the other part of my presentation that I haven't touched on yet is that open data benchmarks, these are all great. These are great steps in that process, but we also need skills. And so from our competition, one of the things that we learned is that a lot of the people that participated in the competition are not actually from the building industry at all. Most of them, in fact, were from other fields, data science and more generic sort of backgrounds. 85%, we did a survey, and 85% of some of the top solutions were not from the built environment. And so this is a problem. We can't get people to do machine learning, or we can't innovate if the humans involved don't have the skills. And so it's also been my mission to help teach Python, which is probably the most popular data science language, to our undergrads and master's students here at NUS. And these are not engineering students. These are not computer science students. These are, in fact, project and facilities management students. So these are students that probably wouldn't usually be exposed to something like data science. We've been able to successfully do that through group projects and various tweaking and tuning to the way coding is actually taught. And it's been really successful, mostly because of the really great tools out there. I mentioned before Jupyter Notebooks, which is the open source platform that we build a lot on. And then Kaggle, of course, is using Jupyter as a template for their notebooks, which is what we also use. So the notebook is a format that is very easy for users to pick up, to sort of clone, to sort of use as a recipe of sorts, and to really, get started and grow with machine learning and data science. So on top of that effort, I also was able to launch an open online course in April of 2020, really aligning, I guess, somehow perfectly with the start of the pandemic across the world. And so a lot of people may be staying home and wanting to learn new skills. And so my team deployed this course, Data Science for Construction, Architecture, and Engineering. And it's been really great seeing people learn new skills. We've had over 20,000 people enrolled in the course over the last year and a half. It's now ongoing. So of course, please check it out if you're interested in learning some Python skills and you're in the built environment. 22,000 people have enrolled so far from all across the world. A lot of people from the US, India, Singapore, UK, and Australia. Those are kind of the big places. And I'm very happy to also be nominated, or our team to be nominated, for one of the edX Prize finalists this year. And so really showing that data science, as applied to certain industries or contexts like built environment, is something valuable and interesting from an educational perspective. So to wrap things up, let's come back to our original analogy with the autonomous vehicle. Okay, so how do we get $100 billion in investment potentially? I've talked about bigger and better open data sets, improving skills of built environment professionals, but also, agreeing upon a big, clear, compelling objective, like autonomous cars, right? So a car that can drive itself. So do we have something like that in the built environment for machine learning objectives? Kind of, not a little bit, not really though. Maybe it's driverless buildings, buildings that sort of heal themselves or something like that. Not sure, but that's something maybe people have questions about in the chat. Of course, I didn't do all this work alone. Here's a slide that's got lots of names on it. And so lots of, in fact, some of the SimberBest other presenters, Stefano and Adrian, were also involved in SimberBest, as well as some of the information about the funding behind a lot of this research. So with that, I'll take any questions or comments at this time.
Thank you very much, Clayton, for this very exciting presentation. I have a quick question, and then I turn it to the audience. Once we do the Kaggle competition, once people come forward, with these amazing solutions, how can I, as a building owner, benefit from that? Tell us about this last step of translation before this know-how actually makes a difference. Absolutely.
That's a great point. And ASHRAE, of course, was the big kind of like prize money supporter. And ASHRAE, of course, everyone knows, is very, very practical. And that was a question I got asked quite a bit before and after the competition. And so the key, one of the things we asked the winning solution, the top 5 winners, to do is to take their solutions, because of course their solutions are extremely complex. So we asked them to break down a much more simplified version of their final solution that has a better complexity versus accuracy balance, in a sense. You don't have that when you win a competition. You have really very, very complex ensembles of models. And so the result of that was actually something that was maybe one of the most important things, was that the winners were able to say, okay, gradient boosting trees as a model is the best type of model for this type of data. And then gradient boosting trees, for example, had started to be looked at in the built environment. People have done some research in that, but it hadn't been adopted by things like, let's say, Energy Star or some of these benchmarking rating systems. And so this competition, I think, kind of nudged those decision makers in those areas to look at, okay, this is probably the best model to choose. Pre-processing of data, this is something that is also very important. So really calling out the conceptually, the really important things that maybe we didn't know before, we now know, but they're not these final solutions, which are super duper complex. The other big value for building, for people in practice, is that if you start to try to develop skills in this area, having young professionals use the generated content, the templates, the notebooks, all these different things as a starting point to learn is extremely important. So in my opinion, as an educator, I think that the actual starter notebooks in the competition are just as valuable, if not more valuable, than the final solutions. So lots of different options to help people get started in learning this stuff is really important. So yeah, but the final solutions, the winning solutions, were really, really complex and very hard to make, into something very practical.
So. And you alluded to the skill gap between across the communities. Exactly. That is very important. So very commendable, the course that you started and efforts like this. I would like to open it to the audience. Please, people, post your questions on the chat or raise your hands if you want to ask live. We have 3 minutes.
Thank you, Clayton, for the presentation. It's a great one. I have a question for some portable application that can be applied to the building data set. So we know that currently brick schema and model data set has a great influence, but one issue is different buildings have different characteristics. So for example, some building doesn't have air temperature sensor. Air temperature is pretty common, but some building just doesn't have that, or they don't have mean radiant temperature, or some equipment, are various across buildings. So how to solve this kind of issue if we want to develop a kind of standardized application, which is similar to some apps on our phone, so everybody can use the one application mostly all phones. In building environment, it is really difficult to develop this kind of effort. Any insight?
Yeah, thanks, Ricky. That's a really great question, and it kind of goes back, I think, to the point I was trying to make about open data sets. So, for example, let's say we had 100 buildings and we had all the BMS data from those 100 buildings, including all the different types of temperatures and sensors and all these different things that we have. And we also have labels. So don't forget, labels is very important. So we know, let's say we're doing fault detection. We have labels for faults. So something similar to ImageNet, right? ImageNet is millions of pictures of cats and dogs and all these things. So that would give us a foundation as a community to come up with methods that could detect different things. We would know how to make a technique portable across 100 buildings because we'd have 100 buildings in the open data set. So I have this dream that we have sort of an ImageNet style. What we did with the competition was one type of data. It was a whole building energy meter. What if we had BMS data from all different things and we had the labels as well? So the ImageNet data set, you could never predict how your algorithm would be applied to airplanes or puppies or kitties if there wasn't those data in that data set to be used. So I think that open data is a big foundation for us as a community to be able to try to do those things. So yeah, maybe a few years from now, we'll have an ImageNet for the built environment, which we don't have yet.